Good evening. So today we will begin the study of the last major topic of this unit and of the class itself, the parametric surfaces. The motivation for this section today is to introduce the last type of integral that we will study in Calculus 3, namely the surface integral. Historically speaking, in my experience, this always seems to be a difficult topic for students, but in my opinion, it's not really as difficult as it seems. The problem with Calculus 3 is that this is the last topic and it's a lot of material that accumulates toward the end. Because you kind of end the class in full speed, with yet another major integral and lots of different setups and bounds to establish all sorts of things you have to learn about any type of integral. However, you can actually make it easier if you pay attention to a couple of analogies that you can make with a line integral. So basically, to anticipate a little bit what comes up later. So remember that the line integral, it's essentially just like a Calculus 1 Riemann integral, with the difference that the domain, instead of being a segment, right, from A to B at closed interval, it's a curve between two position vectors, or between 2 points in space, right, denoted by these position vectors. And then remember the whole thing, we define the line integral, which, two types of it, the line integral over scalar fields, which is denoted like this, or the line integral over vector fields, which is denoted by this, or by f dot dr, if you remember the notations prior. But bottom line is that this is an integral that's evaluated at a curve, or a line, generally speaking. So the surface integral is going to be basically the analogous of this, except that the domain of integration, so later, the domain of integration, I have to be a little bit more careful how I come up with this terminology actually, because the domain itself for integration is going to be actually region in 2D. But the idea is that, let's put it this way, the function to integrate is evaluated on a surface. I think it's more appropriate, because I don't want you to get confused with the actual domain when it's time to in fact solve the integral. So like in the line integral, you evaluate the function at the curve, but once you denote the curve via a parametric, via a vector function, the vector function depends on one parameter with the bounds a and b, or whatever those bounds are, and then you're gonna integrate over t actually, eventually, when you set up that integral. So again, the analogy is that for line integrals, the function, whether it's a scalar function or a vector or a field, is evaluated at a curve, whereas in the case of a surface integral later, the function is going to be evaluated on a surface. So the first thing to do, and this is the topic of today's class, is to actually study surfaces in a more systematic and more general way. We want to define the surface, or to describe the surface as a vector function. For two reasons. First of all, of course, the tool is more efficient using vectors. I mean, we have anything related to vectors at our disposal. And on top of that, it is the most general type of representation for a surface, because you dealt with plenty of surfaces already. For example, the paraboloid z equals x squared plus 4y squared is a surface. And as a matter of fact, you can view any function of two variables as a surface. More generally, you can also view an implicit equation in x, y, z as a surface. So for example, the ellipsoid, an example is x squared plus, let's say, 4y squared plus z squared equals 9 That's another example of a surface. All of these are given in Cartesian coordinates, either as a function of two variables or implicitly as a expression in terms of x, y, and z. But more generally, you can, like I said, you can view a surface as a parametric function or as a vector function, which will include these previous surfaces, but also will cover more general shapes that cannot be easily described in terms of Cartesian coordinates. Okay, so let's get to the point. How do we represent a surface via parameters? Well, the most important thing to remember before we look at the typical notation is that unlike curves or lines, which are of dimension 1, so in other words, they can be described by a single parameter, denoted by t typically. Surfaces are two-dimensional objects. So they represent a subspace essentially of two dimensions in the 3D space. Which, for this reason, that means that you will need a pair of parameters in a what we call parameter domain. So to give you a description, let's say the parameters are denoted by u and v. Okay, so let's say this is basically a region D in the plane. Doesn't matter which one gets to be u or v, I mean horizontal or vertical axis, doesn't matter. And you can call them obviously ST or whatever name, but just to keep some consistency, we're going to call it u and v, the parameters for a surface. So these parameters vary inside a region, the so-called parameter domain. It what used to be the interval from a to b for t in the case of a curve. And for any point in the parameter domain u and v, we're going to associate a position vector to a point on the surface. So imagine here in 3D you have this generic surface, right, in the three-dimensional space. And to any u and v, you're going to associate a position vector, let's say over here, that points to that point on the surface, which will be denoted by r bar, but this time of u and v, instead of just one single parameter. So as a vector function, each surface S is going to be denoted by a vector in 3D whose components depend, or each of them depends on the two parameters. So the components of a vector function which denotes a surface or represents a surface are functions of two variables given by those parameters. So x of uv, y of uv, z of uv. So before we move on with a couple of examples, it's very important to make it easier to see the analogy with the curves. Okay, so previously we had the parameter domain, right? We had, say t between a and b, and then the curve was made of three components, each of them depending on that parameter, right? So that was for curves or lines. But for the surfaces, now the parameter domain has to be a region because you have two parameters, in fact. And as these points vary in the parameter domain, each of them will indicate a position vector on the surface. And then if you vary all the points in the domain D, then these position vectors will describe the entire surface. So that is the most general format for a surface that we can work with in Calculus 3. So let's go over one quick example before we move on to yet more than, well, we're going to have plenty of examples, or at least several examples, right? One of the issue here is that, and let's make sure we, let's keep this in mind as a remark, do not confuse the parameter domain u and v with the actual point on the surface, which is x, y, z, each of them depending on u and v. When you work with actual numbers, there is this tendency for people to get really confused on what's on the surface and what's actually not on the surface. So in fact, it's what's a parameter value. So here's an example. We're going to get back to this in a minute. And I'm not going to specify the domain here. I mean, let's say it's just all pairs of numbers, u and v. So R of uv, let's say it has the components u plus v, u minus v, u plus v squared. I should actually write this. I'm going to write this on the next page as well. So for example, let's see one practice question here. Let's check if a given point is on the surface. So let's check if the point 3, 1, and 3 is on the surface. So the answer would be yes if I can come up with two parameters u and v such that each of these components is equal to 3, 1, and 3 respectively. So then how do I check to see if that's the case? Well, you basically kind of have to solve a system of two equations, or shall I say three equations and two unknowns. So you pick two equations, the easier one you can find. I mean, you can pick any two of them. Let's say the first two. Solve for u and v if it's possible. And if it's possible, check to see if the third equation is matched as well. So for example, in the first two equations, I can add the two. 2u equals 4, u equals 2. And I can easily compute v from the first equation. 3 minus 2 is 1. And we can check the last equation. That's 2 plus 1 squared equals 3. So the answer is yes, this point is on the surface. But again, don't confuse the parameter value corresponding to that point. So the parameter value as a pair is going to be 1 and 2 and 1 in this order, right? U equals 2, v equals 1, right? This is v equals 1. So corresponding to the parameter value 2, 1, we have the point 3, 1, 3 in the surface, which again is given as a position vector. So 3, 1, 3. Okay, so let's move on with another points of discussion on the next page. So I wrote this surface again one more time. Another common questions you may have to address is, can we switch back and forth between parametric and Cartesian format for a surface? That's another important piece of to go over, because even if you, let's say you have a surface which is given in a Cartesian format, you need to write it in the parametric format, for example, before you set up something like a surface integral. There is no strict algorithm on how to do this. Remember, the idea is that if you want to go from parametric to Cartesians, essentially you need to basically remove or to eliminate u and v from, so if you go from parametric to Cartesians, you need to eliminate u and v when you set up each of these components equal to x, y, and v. It's exactly, I hope, again, try to always make this comparison with lines or curves. It's exactly what you did for parametric curves, except that in that case, the algebra was a little bit easier because to go from parametric to Cartesian, you had to eliminate just t. Here I have to eliminate u and v. Usually, again, just like before, when we check the point on the surface, you basically want to solve for u and v in terms of x and y, and then plug it into the third equation, and then solve for z as well. And then you basically, so you end up with an expression in x, y, and z. Sometimes you can recognize the shape as a geometric figure. So again, let's add the first two equations. So from the first two, I get 2u equals x plus y, which gives me u equals x plus y over 2. And then let's go back to the let's say the first equation. from it I get v minus or x minus u, and then replace u with the quantity that we just found, x plus y over 2. Let's simplify this a little bit, x minus y over 2. So v is x minus y over 2, u is x plus y over 2. We bring them together into the last equation. So u plus v squared is x plus y over 2 plus x minus y over 2 quantity squared equals z. So this will be the surface in Cartesian coordinates. So if you see in this case, you basically end up with the surface as a function of x and y. All right, so this is the same surface in x, y, z, right, in Cartesian coordinates. Generally speaking, a surface is going to be a relationship between x, y, and z. It doesn't have to be like z equals a function all the time. I want to point out that you already have seen before a parametric surface. So for example, remember when we did the triple integral, when we solved the triple integral in spherical coordinates. So for example, let's say I'm looking at a circle of radius r equals, or shall I say rho to keep up the notation from the spherical coordinates, rho equals 5. Then we can view that circle as a parametric surface in the parameters given by the two angles. So remember, spherical coordinates are the radius, phi, the angle with the positive z-axis, and theta, the angle between the projection of the point on the xy plane and the positive x-axis. Okay, so just remember how we right. So this is phi, and over here in the xy plane, this will be theta, right? Measured from the positive semi-axis. If the radius is 5, then we can view the circle of radius 5 as a parametric surface with the components radius, which is 5, sine of phi, cosine of theta. Refer back, please, to the relation between the Cartesian coordinates and the spherical coordinates. So these are spherical coordinates. Second component was 5 sine of phi, cosine of sine of theta, and the last component was 5 cosine of 5. Okay, so this is another example of a parametric surface, because it depends on the two parameters, in this case the two angles. Another important remark, notice that any surface given as a function of two variables can be written in the parametric form, and in fact we do that quite often when we deal with surface integrals, in the parametric form where typically, it doesn't have to be, parametrization by the way is not unique, right? But typically x and y are the parameters. So if we want to keep up with notation with u and v, it's like we pick x to be u, y to be v. So of course then the entire surface will have u and v as the first and second component, and f of u, v as the third component. But in practice, you don't even bother actually to write u and v. You can just write r of xy, x, y, f of xy, right? You simply treat the x and y as parameters. That being said, let's move on to another important topic, which again is gonna connect later to the surface integral. Actually, before we do that, let me just go over one more example. Let's actually go, because we dealt with yeah, so we move from parametric to Cartesian coordinates. Let's do another example of the same, a little bit non-standard. So let's say, I mean not non-standard, but slightly more complicated or different than the previous ones. So let's look at the following surface: u cosine of v, u sine of v, and then let's say u squared. Okay, so again, this is x of uv, y of uv, z of uv. So how does that look like in Cartesian coordinates? Solving for u and v, it's not as clear-cut as before, right? Although we had similar examples like this in a different context. Again, if you go back to the memory lane, right, with the parametric curves. You don't want to solve for u in terms of cosine of v and then plug it in here and deal with tangent of v, whatever. Try to exploit some trigonometric formulas. Like, for example, we can notice, just to exploit the fact that cosine squared plus sine squared is 1, which is a typical simplification that you may want to use, we can notice that x squared plus y squared is in fact u squared cosine squared v plus u squared sine squared v. And then if we simplify, if we factor u squared, then the parenthesis becomes 1. But notice also that it's, as it happens, u squared is actually equal to z. So if you look at the beginning and the end, now we recognize that in fact the surface in parametric form is actually a paraboloid. And in retrospect, you kind of see why this parametrization works here, because each section is a circle in this case, so you can recognize in terms of x and y for a given z, those are like polar coordinates for x and y. So let's move on to the next page. The next topic to talk about is the concept of the tangent plane, which, like I said, is going to be used later on when we establish the surface integral. So stay tuned. Okay, so let's see how we can, how do we find the so-called tangent plane to a curve, to a surface, given in parametric format, right? So r of uv given by x of uv, y of uv, z of uv. Well, the idea is really the same as the one we used for a surface given by a function in terms of x and y. So let's say this is the parameter domain D, right? This is where u and v is taken. And then we're looking at a surface, right? A three-dimensional surface, right? In 3D. And we pick a point. The tangent plane is always defined at a point. We pick a point corresponding to a parameter value. Okay, so point here, which is r bar of uv. As we fix either u or v in the parameter domain, so look at the parameter domain, let's say I fix u and I let v vary, or I fix v and I let y vary. So if we do that, we're going to essentially trace two curves on the surface. So for example, in fact, let's actually, to be more precise here, let's say we have a point u naught, v naught, right? As, let's say u is fixed at u naught, right, of one fixed value of u, and v varies. We're going to have presumably one curve corresponding to keeping u fixed and varying v. I don't know how that shape of the curve looks like. We cannot actually assume, see, unlike the previous case with partial x, partial y, we don't know if it's parallel to x or y. It's not in general, right? It's whatever the curve looks like if I fix one of the parameters. If I have only one parameter and vary, that automatically will be a space curve. But with the difference that this lies on a surface. And then similarly, if we fix v and trace the position vector on the surface, that's going to be another curve, u v naught. So these will be curves or space curves. And just like any space curve, depending on one parameter, the derivative with respect to the parameter that varies, it will constitute the tangent vector. So for example, on the one where u varies, this one here, the derivative with respect to u at that point, u naught v naught, is going to be a tangent vector. So ru at u naught v naught will be the tangent vector for the space curve ru u v naught, right? So v naught is fixed. And on the same manner, if I keep u naught fixed and I take partial v, then rv at the same point will be the tangent vector for r, not ru, r of u v naught, and this will be r of u naught v, right, as v varies. Okay, so altogether, these two tangent vectors will form the tangent plane to the surface at the point u naught v naught. All right, so let's actually come up with the equation of such tangent plane, right? Because remember, we have the point. All we need is the normal, right? So if I have two vectors that form the tangent plane, the normal to the tangent plane obviously is going to be the cross product between these two vectors, ru and rv, partial u, partial v. Any order you want, we're going to talk about the order later, I mean when we deal with orientable surfaces, but for now it doesn't actually matter the order of the doing the cross product, right? It's going to be either one or its opposite, right? So for the purpose of finding the equation of the tangent plane, either way is fine. Okay, so let's see how this works with an example. Let's use the previous example, and in fact, let's see, should probably use the same point, right, as before. So in the previous example, we had the surface given by u plus v, u minus v, u plus v squared. And we're looking at the point on the surface given by 313. And remember, this point corresponds to the parameter value 2, 1. So we know that r of 2, 1 is 313. Okay, when we come up with the equation of the plane that goes through a point and has a given normal, this is denoted by x naught, y naught, z naught. You might remember the equation of a plane given by a normal ABC going through the point x naught, y naught, z naught. That's a times x minus x naught plus b, y minus y naught, c, z minus z naught equals 0, right? So that's the equation of any plane going through a point that has a given normal. The only difference is that this normal here is given by ru and rv. So let's go through the steps carefully. It's not difficult computation. Just make sure, the only difficult part is to force yourself to go slow and realize what you're doing at each step. And always remember not to confuse the parameter value with the actual point on the surface. So 2, 1 doesn't refer to a point on the surface. It's just the parameter value. So let's come up with the partial derivatives first. The first tangent vector, ru, partial u of each component, that's 1, 1, and 1. They happen to be constant, need not be constant, but they just happen to be constant. Rv is going to be 1 minus 1, 2v. Evaluate these normal these tangents at the point in question, 2, 1. The first one remains 1, 1, 1 because there's nothing to plug in. And the second one, we're going to have to plug in 1 for v. So it becomes 1 minus 1 and 2. 1 minus 1, let me see. 3, 1, 3. I think I switched, sorry, well, did I switch? Let me 1 second. So u plus v, u minus v, u plus v squared. I want to double check something, give me a second. 2 plus 1, 3, 2 minus 1, 2 plus 1, partial u, all ones, partial v, 1 minus 1, 2v, and the so these 1. Okay, all is good. All right, so let's come up with the cross product for the normal. So the normal will be the cross product between these guys. Let's do that. So that's going to be 2 minus negative 1, that's 3. And then 1 times 2 minus 1, that's 1. And then, no, minus 1, right? So the middle point is 1 times 2 minus 1, and then I change the sign, so that's minus 1. And then finally, 1 times negative 1 minus 1, that's minus 2. So 3 minus 1 minus 2. Okay, so this is the normal vector. The point is 3, 1, 3. And then the tangent plane will be 3. So this is A, B, and C. That's the normal. So 3 x minus 3, because the point is 3, 1, 3, right? So 3 times x minus 3 minus 1 times y minus 1, and then minus 2 times z minus 3 equals 0. So let's simplify it a little bit. 3x minus 9 minus y plus 1 minus 2z plus 6 equals 0. And let's keep the x, y, z on the left. And we get minus 9 plus 1, which is minus 8. Minus 8 plus 6 is 2. To the right, that's 2. Okay, so let's do another example, and then the last topic. Well, there are a couple of more things to talk about. First, you know, the notion of orientation on the surface, and also another major thing on this lesson is finding the area of a surface. So stay tuned for the next page. So I want to write a quick remark just to put things in perspective with what we did before. Remember, if the surface is given as a function of two variables, and you have, let's say, a point on the surface AB, f of AB, remember the equation of the tangent plane was given as f of AB plus partial x at AB, x minus a plus partial y at AB, y minus b. We can recreate this formula if you view the surface in a parametric form. So I'm not going to do the whole thing. I just want to point out that, again, what we deal with right now is just like a generalization of this, right? So if I take this and I view it as a parametric surface with the parameters x and y, then the components of that surface are x, y, f of x, y. So of course, you know, partial x of r will be 1, 0, partial x of little f. Partial y of r will be 0, 1, partial y of little f. And so then when we come up with the normal, which is the cross product of these, you will end up with 0 fy minus fx minus fy, the middle term. and then 1 minus 0, the last term. So the normal, unsurprisingly, is minus fx minus fy1, or if you do the cross product in the reverse order, it will be fx fy minus 1. If you look at the equation of the plane given explicitly like that on the top corner here, if you move the partial x, partial y on the left side, the coefficients of x, y, z will be exactly minus fx minus fy and then 1 for z. Okay, so the next topic, like I said, will be finding the surface area of a surface in parametric form. So how to find the area of a surface in parametric form. We know how to do this for a surface given as a function of two variables, if you remember. And what we have here is exactly the same. It's really the same concept. So, you have a generic surface here. I'm not going to go through all the details, right? You come up with a partition of the parameter domain. You end up with a Riemann sum in which corresponding to a partition. So maybe we should actually illustrate just a little bit, right? So let's say this is the domain, right? The parameter domain in U and V. We do a partition for the parameter domain, and the parameter domain is going to be partitioned into non-overlapping little rectangles. Now, corresponding to each rectangle, you're going to end up with a patch, with a corresponding patch on the surface. Not necessarily in the shape of a rectangle. In fact, most of the time, not in the shape of a rectangle. But that patch can be approximated by the corresponding portion of the tangent plane. So let me actually do this in red color so we can distinguish it here. So that little patch is going to be approximated actually by a parallelogram. So let me actually do it. Let's do it differently. If you zoom in, what you have that on the surface, you have the actual portion on the surface, that patch, and the area of the patch is going to be approximated by the area, I'm exaggerating of course here the relative comparison between the two, is going to be approximated by the area of a small parallelogram given by the tangent vectors Ru and Rv. As I mentioned before, this is an oversimplification because I don't want to take too much time to go with the Riemann sum and in all the details like we did it for the double integral in the beginning when we started the first multiple integral, right, corresponding to Calc 3. So when you take the limit of the Riemann sum, each patch can be approximated by an area of a parallelogram, which is given by these tangent vectors. Meaning that what you integrate to come up with the surface area is the area of this parallelogram, which is given by the magnitude of the cross product of Ru and Rv. So remember from geometrical interpretations of the cross product, if you take the magnitude of the cross product, that is actually the area of the parallelogram formed by these vectors. So the surface area will be the double integral, because you obviously vary V on the parameter domain, the double integral of the magnitude of Ru cross Rv, dA. And I want to point out that this is basically exactly what you did in the case of a function of two variables. So you might remember that for a function of two variables, right, if the surface is given as z equals f of xy, the surface area was the double integral of square root of 1 plus fx squared plus fy squared. But in fact, if you look at the normal over here, that is exactly the magnitude of that normal. So it's the magnitude, in other words, of Rx cross Ry. All we have here in terms of U and V is basically the generalization of the same type of formula. So in other words, if you want to save only one formula, then this one in parametric form in U and V is the most general one. Okay, so let's do an example. Two examples, in fact. Let's start over here on the... Let's do first an example for which we don't actually need to sketch anything. So suppose I want to find the area of the surface given by u cosine of v, u sine of v, and v. And the parameter domain is a rectangle. So u between 0 and 1, and v between 0 and pi. Okay, so we need to come up with Ru cross Rv and the magnitude. So let's do it step by step. Ru will be 1 cosine of v, 1 sine of v, and 0. That's partial u. And then partial v will be minus u sine of v, u cosine of v, and 1. So we're going to integrate the cross product. Let's do the cross product first of these. We have sine v times 1 minus 0. That's the first component. Middle component is cosine of v times 1 minus 0 with a sign change, so minus cosine of v. And the last component is u cosine squared v minus negative u sine squared, which makes it plus, it's just u, plus u sine squared v. And look carefully that this actually simplifies to sine v minus cosine of v and u, because, you know, sine squared v plus cosine squared v is 1. So the surface area will be the double integral of the magnitude of this, which is square root of sine squared v plus cosine squared v plus u squared dA, which is the double integral of square root of 1 plus u squared dA. Since this is a rectangle, we can just integrate it in any order we want. So that splits into the integral from 0 to 1 square root of 1 plus u squared du multiplied by the integral from 0 to pi of 1 dv. So I'm going to just give you the first one with maple. It's a little bit tedious to compute via trig substitutions. So the first one ends up being 1/2 square root of 2 plus pi over 2. And the integral from 0 to pi of 1 dv is obviously pi. And then approximately this should be 3.61. So that's the surface area of this surface, right, over this domain. Let's do another example, and then we'll talk about, on the last part, some concepts related to orientation of surfaces. All right, so here's another example. Suppose I need to find the area of the portion of the plane x plus 2y plus 3z equals 6 in the so-called first octant. That's a fancier way of saying that you want x, y, and z positive. So in the positive region of the three-dimensional space. Okay, so like I said, the difficulty or the nuance is in setting up the integrals. Don't rush to set up integrals before you're sure what you're doing. And so let's break down the problem in elementary steps, right? So we have a tool of, I mean, in this case, you could actually treat this as a function of two variables, but let's work in terms of parametric functions. I could get z by itself, so you end up with a function of two variables. But if we want to use the frame of a parametric function, we don't have to choose x and y as the parameters. We have the freedom to do that however we like, right? So in fact, like I said before, if you move from Cartesian to parametric format for a surface, you can pick any two to be u and v, any two of these coordinates, x, y, and z. So for example, I might actually prefer to use u and z as the parameter just to avoid fractions. If I choose x to be u and y to be v, then I have to solve for z and I'll involve fractions. Then maybe that looks a little bit too tedious, not the end of the world, but again, we don't need to choose x and y to be the parameter. So let's choose y to be the parameter u, and then z the parameter v. Okay, now we have to be careful to see what's the parameter domain. Remember, the condition is that x, y, and z should be positive. So if z is equals v, then automatically from the surface, x is going to be 6 minus 2y, which is 2u, minus 3z, which is 3v. So the surface, this plane in parametric format, and be careful to write the components in the correct order. So the first component, the x component, is actually 6 minus 2u minus 3v. Second component, y, is going to be u, and the third component, z, will be v. Okay, so the parameters u and v don't have to be in the same order like u and v in the components. All you know is that each three components depend on u and v in any order they like. Okay, what's the parameter domain? Well, because y is 0, because y is greater than 0, automatically u is greater than 0. Because v is greater than 0, z is greater than 0, sorry, automatically v is greater than 0. And because x is greater than 0, that means 6 minus 2u minus 3v should be greater than 0 as well. And I have to sketch and look to see the shape of the parameter domain. And if you look carefully, that's going to be actually the interior of a triangle. If we sketch the parameter domain, we have u greater than 0, v greater than 0, and this guy here, 2u plus 3v less than or equal to 6, tells you that you're actually below the line 2y plus 3v equals 6, right? So if we sketch this line, if we sketch 2u plus 3v equals 6, notice that the, if you plug in 0, 0 for u and v, you are in the right side of the inequality. I mean, each line separates the plane in two regions, right? And then one of them will make the line positive. I mean, the expression 6 minus 2u minus 3v positive or negative. So you want to be in the positive region. So if I replace u and v with 0, 0, 0, that means the origin is on that correct side of the line. So that means you are below the line 2u plus 3v equals 6. So let's sketch this line. It goes through the points 3, 0, and 0, 2. Like that, right? So if v is 0, u is 3, and then if u is 0, v is 2. So the line here is 2u plus 3v equals 6. Okay, now finally we move on to set up the surface area. Let's do it in one step, right? So that's going to be the double integral over this domain given by the interior of this triangle. Of the magnitude of Ru cross Rv. So let's establish what we integrate, and then we're going to split it. We're going to do it via Fubini's theorem. So Ru is going to be, well, as a matter of fact, let's actually take it separately because we have to do a cross product anyway. So Ru, partial u, is going to be minus 2, 1, and 0. Rv, because these are linear terms, all the partials will be constants. And Rv is going to be minus 3, 0, and 1. Okay, the cross product, and now we can put it in the integral. The cross product between Ru and Rv, that's going to be, first component is 1. Then 2, minus 2 times 1 and sign change. And then the last one is going to be 0 minus negative 3, that's 3. One, two, three. And we have to integrate the magnitude of this. So basically we have to integrate the square root of 1 plus 4 plus 9 dA. And now we have to set it up via Fubini's theorem. Let's do it as a type 1 integral. Doesn't matter as much which way. So now on the outside we have the bounds for u, which are from 0 to 3. And on the inside the bounds for v, which run from 0 to whatever v is on the equation of that line. On the equation of that line, v is 6 minus 2u over 3. 6 minus 2u over 3 is the upper bound of v. And then we integrate square root of 14 v du in this order. Root 14 is a constant, so v between those bounds, that's 6 minus 2 over 3. Let's split that into 6 over 3, which is 2 minus 2 over 3u du. And then finally, we finish the integral 2u minus 2 over 3 u squared over 2 between 0 and 3. So that makes it 6 minus 9, 9 over 3. That's 3 root 14. All right, so that's the area of the portion of the plane in the positive region of the space. Okay, so I think at this time let's talk about briefly, we'll get into more details actually when we deal with the surface integral. Let's talk about the concept of orientable surface. So the main ingredient for a surface integral is the so-called orientable surface. As with other things in this class, I like to actually not overspend too much time on this and give you a very intuitive understanding of it. There are different ways to actually, so there is a formal, more abstract definition of what is an orientable surface, which I'm not going to get into, and plenty other intuitive descriptions with various degrees of intuition, so to speak. Roughly speaking, the orientable surface is a surface where we can consistently choose one side versus the other. So in other words, those are actually surfaces with two sides. That doesn't say much unless we get into more details to describe the whole concept, because lots of surfaces you can imagine have two sides, so you may wonder what are we talking about, right? Because it seems that everything it has two surfaces. So perhaps, or two sides, sorry. So perhaps we should basically mention, I'm not going to actually have another part of this lesson to show you on the internet, because it's a very simple thing to look for. Let's look at or you should look at the classical example of a non-orientable surface, which is basically one-sided. So it has only one side, and that is the so-called Mobius strip. You can obtain one if you have a band, cut a band of a paper, twist it in the middle, and glue the ends, and that's going to be a Mobius strip. Most people probably already have these examples in their mind. I mean, if they look it up on the internet or have seen it before. But I mean, the reason why the Mobius strip has, the way to actually check or convince yourself that the Mobius strip has only one side in some sense. We have to talk about what we mean by one side in a moment. But intuitively, if you start at a point and you walk on the surface, you're going to basically come back to the original point you started with without falling over, so to speak. So you can walk and cover the entire surface. You're not going to leave any point untouched on that surface. And you're going to come back on the original point. In fact, you're going to go back to the original point without falling over the edge. And actually, at one point, in the opposite orientation, basically. So, you know, let's say you are at this point, you start at this point in this orientation, you walk on the Mobius strip, and at some point you're going to end up at the same point but flipped backwards. And if you can continue to walk, of course, you're going to come back into the same orientation the way you started with. So, or put it differently, if you actually walk on the Mobius strip with a paint and you walk without stopping, you're going to see that every single piece of the surface is going to be covered in paint. There is no side that is actually not touched by the paint. But I mean, in a more slightly more mathematical way of putting it, and again, I'll mention the reason in a moment why do we have this discussion here with orientable surfaces. Slightly more mathematical way of putting it is, if you look at the surface, let's imagine you have a surface like that. To be orientable, it means to be able to actually choose a normal vector that you can actually deform continuously and cover the entire surface. So basically, an orientable surface allows you to create a normal field. So vector field made by normals, a continuous vector field in which any 2 points can be, any point can be approached from another point by deforming continuously that normal, by changing continuously that normal. The Mobius strip doesn't qualify because if you do this continuous variation of any normal you pick, at some point you're going to end up with a normal opposite to the previous one, which by definition means is not continuous because you have the opposite of the previous one. So there is no in other words, there is no consistent choice of a side via this normal field, right? It's not going to be clear which side is which. So obviously, if it's orientable, you can have the normal field pointing in one side of the surface, and of course, if you take the opposite of this normal field, all of them will be pointing on the other side of the surface. So in a nutshell, this normal field, which can be constructed for the surface, allows you to consistently choose one side of the surface as opposed to other. To be honest with you, for the goals of this class, we don't need to go that deep into the concept of orientable surfaces, because like I said, what we cover in this class in the concept of a surface integral, the reason we choose these orientable surfaces is because typically the surface integral over a vector field, one applications of it is to calculate the so-called flux across the surface. So for example, let's say you are in some sort of a vector fluid field, in which, like a velocity field, right, in which each vector denotes the quantity of fluid that goes to that point, or the velocity of the fluid going through that point. And you have some sort of a mesh or a permeable surface, right, immersed in the fluid. And you want to calculate, let's say, how much of the fluid goes from one side of the surface to another. Like I said, the flux across the surface. So notice that unless the surface is actually orientable, this statement, the flux or the quantity of the fluid across the surface, is kind of meaningless. It's kind of undefined, right? You need to actually talk about consistently what we mean by a side versus the other. And the way we define the integral, the surface integral in this case, is we're going to choose a side by consistently choosing a normal to the surface in one side versus the other. So when we define the surface integral, we make a choice for the normal. The choice of the normal is usually specified in the problem, and compute the surface integral. Should we want the flux in the opposite direction, it's just a matter of changing the sign of that integral. But again, we have to make a choice in order to actually define the concept, okay, what we mean by the flux between one surface to another. Now notice that the answer may be positive or negative. That's not to say that it's positive this way or negative in the other direction. because it depends on how much flux goes from one side to another, right? The idea is that whatever the flux is along this side is going to be the opposite of the flux on the other side. Sometimes it can be confusing on when you read those problems, like, you know, compute a surface integral for this paraboloid oriented to the right or to the left, and you need to know something about the geometry and then carefully pick the normal in the correct orientation. But we'll get to that when the time comes, when we learn the surface integral on the next lesson. So that's it for today.